Got the recording, so we'll see if it works. If not, it's my first test to try to get that to work today. So I want to talk about section 2.3, which is the piecewise defined functions. And so that's kind of the direction that I'm going to go, and I'm going to follow my way through your notes. So today's thing, and normally I don't do a regular lecture, but I really feel like a regular lecture is important for this particular topic. And I noticed when I'd asked you if you had actually seen this topic before that you had said that you had not. So I think we've connected over, and I think that you can see my sheets now, correct? That's kind of important today to do. So a piecewise defined function is actually a function that's going to be defined using one or more other functions. So it might be, in kind of a real world situation, it might be, okay, we do something for a period of time, and then when we get to a new place, we do something else. And so here's a real world example that would be a piecewise defined function. You're driving your car to school, and we want to do some sort of a graph between time and distance from home. So you're driving your car to school, and suppose you could drive a constant speed. Well, you're going to actually have, so if you were driving and you were doing distance from home, initially you're right at home, so your distance to home is 0. And then you drive to school. So if you could drive a constant speed, your drive to school might look like this, and suppose it's 5 miles to school. And I know it's not realistic. Once you get to town, the speeds change and da-da-da, but play along with me for now. Then once you get to school, you're in school all day long, and so your car's distance from home doesn't change. And then we'll make this really simple. Then suppose after school you drive home. And suppose it's kind of the same speed. The graph I just drew is actually a piecewise function, because in order for me to write a function, in order to write equations that would direct us what to do, I would need to have an equation for the trip to school, an equation for the time at school, and an equation for the trip home. And so I would need to talk about the day in 3 different pieces. That's probably as close a real-world example to what you would experience as I could come up with. Other real-world examples that are fairly common, the price to mail things. If you mail a letter, we all know that it costs 40 whatever cents, 49 cents, whatever it might be, for a letter. But once it gets to a certain weight, the post office charges us more, and for a period of time on that weight, or for a period of weights, it's a new charge. And then again and again, as things get heavier and heavier, that we get these new, almost like a step type of function. The income tax schedule is the same way. If you make up to a certain amount of money, you're charged a particular rate, and then once you get to the next, then it's a different rate, and it's a different rate. And so there's a lot of things in the real world that are defined in pieces, that one equation doesn't match forever and ever and ever. And so that's kind of the logic between this. So in your notes, I actually put, this is actually the textbook. Maybe I'll pull out the notes as well. I just realized I pulled out the textbook piece here. That's what was on top of my things. Let's do both at the same time. Get to the right page here. So both of these are going to look kind of the same. Here's the actual notes version. So again, what we'll see is kind of this, that they're defined with different functions on different parts. So maybe I'll just use those for right now. This is what a piecewise defined function looks like. It's one example of what it might look like. We tend to use the function notation f at x. We use the curly brace. And then we'll have multiple lines in that curly brace. In this case, it only has 2. And what happens is this part tells us kind of the first function to use and the domain we use it on. This part tells us, again, the function we use, and then the domain we use that on. So this is the notation. So what you'll always see is something that looks like f at x equals, and I'm going to write it this way, kind of f1 at x, and then a second function at x, and then what we really have is kind of domain 1 and domain 2. That's what that chicken scratch is. So you have f1 at x, f2 at x, and then domain 1 and domain 2. And these domains may not overlap. We're not going to make the domains overlap. And so if you're like, what do you mean by that? If we come over here and look at my two domains, notice this first one says for x less than or equal to 0, and this one's x is greater than 0. So these two domains have no overlap. This one stops and equals 0. This one picks up just to the right of 0. So we don't want to have any overlap. So you'll never see me do less than or equal to 0, greater than or equal to 0. One of them, if they meet right up, one of them will have equality and one of them won't, every single time. So I wanted to talk a little bit about kind of the anatomy of this. Now, there's nothing magical about two pieces. In fact, if I flip over, and I'll come back, but if I flip over, here's one that has 3 pieces. We could have lots and lots and lots of pieces. Usually if you can do these problems for 2 or 3 pieces, you could do it for 12 pieces. It's just it makes more work. So when I look at something like this, I'm going to do a little baby step before I actually look at what's in the notes. What I need to be able to do are a couple of things. If you're given this, I need to be able to graph, and I also need to be able to compute. So let's do a couple of computations, and I'm going to do the graph a little bit differently than what I even put in the notes. If I had this function, and I asked you to do f, and I'm going to do it this way, f at positive 5. At first I was going to do a negative number, but I'm going to do f at positive 5. What I have to do is I have to say, okay, take out the plus so it's less confusing for you. I have to look at this and say, okay, which line do I use? Because if I do a computation with a piecewise defined function, I do not plug that number into every piece. I only plug it into the piece that is appropriate. Or in other words, the piece, I figure out, is this 5 part of domain 1? Or is that piece part of or is that 5 part of domain 2? And so I ask myself, is that a domain 1 or a domain 2 number? And so in this case, does that go with my first domain or my second domain? Second. Why is it my second? You're right, by the way.
It's greater than 0.
It's greater than 0. Basically, to figure out which domain it is, think of plugging the 5 in here and looking for the true statement. 5 is not less than or equal to 0, so it does not apply to the first line, but 5 is greater than 0. And so it does apply to the second line. And so if I wanted to do f at 5, then I just plug the 5 in like I would any other x number, and I do 5 plus 1 is 6. So f at 5 is 6. I'm going to ask one of those dangerous math teacher questions. Is there anybody that, when I just did that, said, I don't have a clue where she just came up with that number? Are we all okay with that one? Well, what if I now wanted to do f at negative 3? Do I again use domain 2 for this one? No, this time I use domain 1 because negative 3 is less than or equal to 0. So this tells me to use the first line, and in the first line there's no place to plug in the number negative 3. Remember, this is actually a function that then is always just equal to 2. Always just equal to 2. No matter what x is, I get a 2 out as long as the x is less than or equal to 0. Let's do one more, and we'll see some more of this in the notes. Suppose I wanted to do f at 0. Now notice f at 0 is where the two pieces kind of break. That's where the one ends and the other one begins. So which one do I use? Domain 1 or domain 2? Domain 1, because that's the one that has the equality. And so therefore, what would f at 0 be? 2. Sometimes students think they're going to outsmart the faculty member. Okay? So sometimes they think they're going to outsmart me. And they're like, I'm just going to plug into all the lines, and I'll at least have one of the answers right, so she's probably going to give me some partial credit. No, because the whole purpose here is to know which line of the piece, which piece that number gets substituted in for. And so putting it into all of them isn't going to get you credit. So the important piece is to know which one to plug into. For most students, that's not a problem. Most of you will kind of get that. The computation part isn't the problem. This is usually, any of the questions I would ask, this is usually the easy one. So let's go back. And then what we might want to do is, I'm going to break into this, is we might want to graph this function. Graph this piecewise function. So I did this is the way I initially did this, and now I'll show you kind of what I actually do. This isn't, quite frankly, the way that I do it when I'm doing the process out. So what I do though is I take each of the pieces, and I made them y equals, so I graphed them. So the first line is actually y equals 2. So instead of using f at x, I just put a y in. Y equals 2 for x less than or equal to 0. And then the second piece becomes y equals x plus 1 for x greater than 0. So y equals 2, hopefully you all remember from what you did in the last chapter. Y equals 2 is just a horizontal line. And so here's what y equals 2 would look like for x less than or equal to 0. And I'm going to make one addition to the graph that's here. I'm going to put a big fat closed circle there because it has equality. And so I'm going to make sure that I put an equality filled in dot there. So that's what that first piece says to us. It says graph y equals 2, but stop at 0. So do it for all the numbers less than 0 and stop. Now the neat part is you could do that on your calculator, right? You could put y1 equals 2 in your calculator. You just need to realize when you translate that to a piece of paper that we don't want the part that's to the right of the y-axis. Then we do the same thing for x plus 1. So we do y equals x plus 1, and this time it's greater than 0. And technically, because I don't have equality to, that second piece, if I were going to do it, has an open circle, because I don't have the equality. Now, unfortunately, that's not the answer. What the answer is I want to do a single graph. So I take these two, and I merge them together into a single graph. So all I've done is taken those two pieces, merged them into a second graph, or into a third graph, if you want to think of it that way, and that becomes the piecewise. Now, I'm going to tell you, that's sophisticated. That's the math teacher way of doing it. Now, for the student who's new at this, here's what I typically do. I typically suggest that you make a couple of tables. Back to, third grade or whenever you started making these function tables, that you make a couple of tables. One of them is the y equals 2 for x less than or equal to 0. And so what I just do is I pick a bunch of x's that fit in fit this domain. So x's that are less than or equal to 0. So 0, -1, -2, -3, -4, whatever you want to make. It's a line, we probably don't need too many points. And what we know is, with that kind of a line, if x is anything, y is always 2. And so if I were then graphing this, I wouldn't do these first two. I would actually go, okay, I have some points. I have 0, 2, I have -1, 2, no, -2, 2. No, I might have all these values, however I've plotted them on here. And then I connect them with the line that I know they are. Technically, and it's just the way the calculator program I used it, technically there's an arrow, it keeps going to the left forever. Then I can do the same thing for the second piece. The second piece is y equals x plus 1 for x greater than 0. And typically if I ask you, oh, give me some numbers greater than 0, usually you'll tell me 1, 2, 3, 4. And we plug in, we get 2, 3, 4, and 5. And then what I suggest you do, and this is kind of the Jerry way of doing this, is we need to do one of two things. We either need to pick a number that's really close to 0, you know, like 0.000000000, I don't know how many zeros I put. And I'm going to have 1 point, you know, just don't quote me, I may have the wrong number of zeros, but I'm going to have 1 with the same number of zeros, and then the last digit being a 1. What I in reality do, this is what the math teacher in me needs to say, what I do in reality is I pick the number 0 and I say, oh, if I could pick the number 0, it would give me the number 1. And this is my own personal notation. Around that particular point, I put in my own mind an open circle. And so when you see me circle that, that's my reminder to myself that that point isn't really a point on the graph, it's an open circle point. Again, that's my technique for doing it. The real math teacher in me says we pick something really close to 0, and we go, oh, we're really close to 1, and so we're coming in and approaching 1. I tend to do this 0, 1, and then I realize that is actually where the open circle is. And then I plot all the other points and recognize it's a line and I draw it. Most students with a fair amount of practice don't have a problem with this. But it does take a little practice when you haven't seen it before. So we graph each piece separately and we merge them using only the appropriate domain. And I apologize if that seems really simple to some of you, because for some students they're like, okay, I get it. You don't need to go through a bazillion examples. But I know there's always some that I do. So then I have a couple more examples, and these I'm not going to necessarily run through, but I want to point you to them, because there is something I really want to get to with these. So I did a couple more that are just the evaluates. And so make sure you read these and you feel comfortable with the evaluation that I did. And so and you'll notice that although I didn't talk about domain 1 or domain 2, I talked about the domain of the first piece or the domain of the second piece. So you can think of those as domain 1 and domain 2, line 1, line 2. And I did the same type of thing here with the first piece, the second piece, and the third piece. So make sure you feel comfortable with them. I know for probably virtually everyone, that once they read those, they're going to be like, yep, I have that. You're all intelligent people. You wouldn't be in my class if you weren't. Your schools don't typically let just anybody jump in here. You've all had some history of being pretty good in math. So then I did, and I almost did overkill in this section. So then I did another graph, and this time I did a graph that has 3 pieces. And again, I ran through the same process I did before that I did on the first page, because I'm doing a legitimate math way. So again, and so what you'll see I do sometimes if I do these problems is I number those 1, 2, and 3. And so here's 1, here's 2, and here's 3. And typically, again, if I were doing this without my calculator, which is most often the way I do them, is I actually make a little table. And the nice thing is, y equals 2x plus 1, I feel pretty good about the line. And so to draw a line, I only need 2 points, maybe 3. This one says for 0 to 1. So I might use 0, I might use 0.5, and I'm going to use 1, but notice I don't have equality. So when I use the 1, that's going to be my open circle. So I do the math. So let's see, if I do 0, that gives me -1. If I do 0.5, that gives me 0. And if I do 1, that gives me 1. And so you'll notice, I'll throw the open circle on. I graphed that. So there's my 3 points. I knew it was a line. Similarly, I'm going to jump over to 3. Similarly, I know that's a line. And this is for greater than 2. So again, I'm going to use 2, that ending point. But I know that that has to be an open circle because of just the greater than. So I might use 2, 3, 4. So if I do that, that's going to give me 4, 5, 6. And now I didn't draw it far enough to get that, but here's my point 24. That would have an open circle. And that piece would go on forever. It's greater than 2. Notice this one actually stops here because it said 0 is the low point. So my domain actually stops at 0. And then in the middle, y equals x squared. Hopefully you recognize that's your basic boring parabola. It's a little bit trickier because it's a small domain. So maybe I'll use 1, 1.5, and 2, and I square it, so that's 1 and 4 and 2.25. And so there's my, and I have equality, so both ends have a dot, have a closed circle. And just if you want to check me, there's that 1 and that 2.25. So it looks like my graph is pretty decent there. And then we suck all those up into one graph. And in this case, you'll notice, unlike the previous graph, you'll notice these pieces actually match up. They actually meet each other. So notice that this open circle is at 1, 1, and notice the closed circle, I don't want to put a circle around it. The closed circle is at 1, 1. Notice here I have a closed circle at 2, 4, and I have an open circle at 2, 4. Kind of like genetics, the closed circle dominates. So if you have a closed circle in an open circle, the circle's closed. So brown eye, blue eye, brown eyes we all have. Closed circle is the dominant feature. Please do not do this. Don't draw a closed circle with an open circle around it. No, bad. No eyeballs, please. So we graph that. As the next Wiley goes live, I'm trying to consciously not pick the questions that ask you to graph. Wiley's fixed a lot of it so that they don't have as many graphing questions. Sometimes that causes students great stress because if you don't graph it just right with your mouse, it doesn't mark it right. So I'm going to try not to give you any Wiley questions where you have to physically graph. If there's any Wiley ones with a graph, it'll be an A, B, C, D, pick the right graph. I will by hand be asking you to do some of these. So I'm going to come back. I'm going to come back to this example because I want to talk about this one right here. And I actually may pull out the actual textbook and do an example or two. So here's kind of a hard, for most students, this is the hard question. This is usually the one that causes all kinds of trouble. Okay? the hard question, and what's here is, so I'll come back and I'll hit this other piece, but what's here is I have this particular graph. So suppose I have that graph, and what I want to do is the part B of this. I want to determine a piecewise function for that graph. So what I typically do is I look and I go, hey, self, it looks like there's two pieces. So the first thing that I notice is there's two pieces. So as soon as I know there's two pieces, if I'm going to make a graph, or make a function, by the way, this has time, so I'm going to use t instead of x. What I know is if I have two pieces, that's what my final answer needs to look like. And I need to have everything you see there. I need to have the f at t, I need the equals, I need the curly brace, and I need to fill in everything that's on those lines. So I need to figure out the lines. And remember, these are all the domains, and these are the actual function pieces. So, I look at my two pieces. This is piece 1. It's piece 2. Right? Piece 1 and piece 2. Quite honestly, piece 2 is quite a bit easier, right? If we look at the graph and we look at piece 2, it's a line, right? And it's a special kind of line, it's horizontal. And the beauty of a horizontal line, as we saw in one of the previous examples, is a horizontal line, just to remind us that all horizontal lines are of the form y equals some number. So I'm going to cheat because I actually have the table up above. When I look at the table, so I don't have to count all those little boxes, when I look at the table up above, I can pretty clearly see that y is always what number? 18. Yeah. So in here I put the 18 because that's the horizontal line. That's that. Then I just have to figure out, based upon my counting, where the domain starts. So remember, the domain runs along the horizontal axis. So what's my smallest input number that seems to be used here? For this line. I think it's 3. Do we all see that it's actually that 3 seems to be? And so, and if we read the example, we'd actually see this doesn't have an arrow on the end, it's actually ending. And the table actually tells us where to end. And so in this case, this is actually telling us we're going to end at 14. And I need to put some stuff in between. But my domain starts at 3, it ends at 14. Unfortunately for these, we don't use interval notation. We tend to use inequality notation. Since I have a fixed start and a fixed end, that means I'm going to have these symbols or something similar to them. And if I actually read the question, like I said, my variable is t. Now, I haven't put equality on either of these yet. I'm going to wait and do the equality at the very end. So realize that if you look down, you're like, wait a minute, that 14 has an equality when you showed me the answer on the bottom. We'll come back to that, I promise. Now I need to do this piece. And this piece I recognize as what? What kind of an animal is that? That's supposed to be an easy question. What shape is that? It's a straight line. Yep, it's a straight line with a positive slope, negative slope, zero slope. What kind of a slope? positive slope. So I need to write the equation of this line. So I pick my favorite 2 points. So it's a line. I pick my favorite 2 points, which by now you're all really good at. By the way, the part A that I didn't do, we have a table, so you pick any 2 points, and what you would learn is if you picked any 2 points, the slope is 4. From the table, we can see the y-intercept is 6. So the equation here, if I were doing it with x's and y's, the equation here would be y equals 4x plus 6. We have t's instead of x's. So I might pick 4t plus 6. By the way, you'll notice if you look down, I just wrote it as 6 plus 4t. It doesn't really matter which order. And now I need the domain for this piece, and I'm going to tell you that this one also is going to have a closed dot on this end. So now I look at that first piece, I look at that particular one, I go, what's the smallest x or t that we use to make that line? 0. What's the biggest t that I'm using? Where does that line end? At what t? I heard somebody mumble at 3. And again, the t's are going to roam from one to the other. If we read the wording of the question, or if you even use the graph that we have here, hopefully if you look at the way I drew the graph, you recognize that I need equality at 0 because I put the closed dot at the very beginning, and I have equality at 14 because I put the closed dot at the right end. Now the question becomes what I do at 3. Now remember, my domains can't overlap. So I can't do equal, because then I have an overlapping domain, and I don't want to do that. Even though in this situation, it's not necessarily going to matter. We never write it with an overlapping domain. So what we do is we pick. We either put the equality on the first 3, or we put it on the second 3. If the 2 pieces match, it does not matter. You just pick one. So you might put the equality on the first 3, and the person sitting next to you might choose to put it on the second 3. Does not matter if the pieces match. You're both correct. It's important if the pieces don't meet because you do have to put the equality on the piece that counts. And you have to put the not equality on the one with the open circle. If that's the case of what we have there. This is a lot of work, right? Again, you notice there's 2 pieces. So we need the domain for each of the 2 pieces, and then we need to write the equation. This is the part I'm most concerned about, and it's the part that I wanted to make sure that I got to. So, let's do a couple of these, and I'm going to actually do an odd question. I'm going to do some odd questions here. I want to look at this question 5. This is actually from the book, section 2.3. I want to write the formula. So what's one thing I noticed? So let's see, Copenhagen, you look at that graph. What's just one thing you observe?
There's one open circle.
An open circle. Yeah, in other words, and I'm going to ask kind of a leading question. Do those 2 pieces meet? Do they meet right up and so you stop and you start without lifting your pencil? So if I asked you to draw these right here, could you draw this whole graph from here over to here without lifting your pencil? No. So that tells me that I have some sort of what we call a jump in there. So yeah. So that's good that there's one open circle. So that's going to be important because that tells me I'm going to have just inequality someplace. Excellent point. Sackets, is there something else that you notice? Oh, they don't notice anything. They don't want to talk to me today. I'll ask a leading question. How many pieces are there, Sackets? 2. There's 2 pieces. So yeah, so there are 2 pieces. So when I go to write this, it's going to be similar to what I just had. Right? There's my 2 pieces. Alex Bay, when I go to write those pieces, what am I going to be writing equations of? Lines. So I'm going to be writing 2 equations of 2 lines. So I'm going to have kind of, and I don't need the y equals, but I'm going to be having kind of an m1x plus a b1 and an m2x plus a b2. So I'm going to have slope x plus a number, slope x plus a number. So I'm going to label these just so that we're good with our notes. I'm going to call these piece 1 and piece 2. So this one's going to be piece 1 and piece 2. And when your book does this, if they don't put the closed dots on the end, they typically want us to think of those as arrows. So if I'm on piece 1, what is the domain of piece 1? So let's see, Alex Bay, anybody want to help me out on what the domain is for piece 1?
X is less than 3.
X is less than 3. Very good. Thank you. And you use less than because Copenhagen told us that there's an open circle, right? Yeah. So, Sackets Harbor. You want to help me with the domain of piece 2? Yeah, x would be greater than, and is it greater than or greater than or equal to? Yep, greater than or equal to what number? 3, yep. So this piece ends at 3, given this, notice this point. This piece starts back up at 3. The one doesn't include the 3, the other one does include the 3. So all of these here are piece 1 values up to here, and then we pick up and these are all piece 2 values. For many students, that's actually the hardest part of the problem because they're pretty good at writing equations of lines. So now I have to write the equation of the lines. I claim piece 1's line is a little bit easier. Why do you think I think it's a little bit easier? Yeah, I think I heard somebody mumble it. I know the y-intercept, don't I? So piece 1 is something x plus 5, isn't it? But then I just have to use my 2 points and find the slope. And I can use either 0, 5 and 1, 4 or 1, 4 and 3, 2. Either way, I think when I do the slope, I get the number -1. Is my math okay? Does everybody agree that the slope is -1? I need to be watched. And then I do the same thing here. Please don't do this. I get some students that they do this. They try to like extend the line, and they try to guess what the y-intercept is. Please don't do that. Right? Go through the pain of actually doing the math out. So if I do the slope, this has a positive slope, so it looks like the change in y and the change in x. So my change in y is 1, and my change in x is 2. My math look okay there? Yes, okay, good. So I know I have this. I'm pretty sure when I get done, it's gonna be 1/2 x minus some number, so let's just kind of crank that through. So y equals 1/2 x plus b, I'll do the plus b. Boy, both points are not necessarily fun, they have decimals, so I'll use this first one. 0.5 is 1/2 times 3 plus b. 0.5 is 1.5 plus b. So b is -1. My math look okay? And there we go. We've written that. The math teacher may have just made that look really, really, really easy. I apologize. It's not. If you just went this, you're like, oh, that's easy. If you don't go and try to do a few of these, and I on purpose did this odd question so that you could go back to your own notes. You go back and try it and see if you can make the answer match. You really need to make sure that you practice these. Make sense? I'm going to do a couple of other book questions. You notice I'm going to do a couple of odd questions. And I want to kind of talk through those. So let's look at question 9 for a second. Question 9 says, find the domain and the range. On these questions, the domain is pretty easy. Because all we do is we look here and we go, okay, according to those two lines, what numbers should I use? Well, I can use everything less than -1 and everything bigger than or equal to -1. So if I put those two together, what's that tell me? All real numbers. Right, so that one, the domain is all real numbers, -infinity to infinity. Because if you're like, okay, how could I write that to myself? Well, -1 seems to be important. The piece 1 says use those. The piece 2 says fill in the dot and use all those. So now I see the entire number line. Right? Because there's piece 1, there's piece 2. And the two together give me the whole number line. The range is a little bit trickier because we have to physically look at the graph. At least for me, I want to physically look at the graph. So if I were going to physically look at the graph, I have this first piece, and so I'm going to do my little charts here. So I'm going to pick things less than -1, and I am going to use -1, just knowing that that's my open circle. So if I use -1 in here, that's going to give me 0. If I use -2, that gives me -1. If I use -3, that gives me -2. So -1, 0, open circle. -1, and then -3 is going to give me -2. Then the other one's going to be x squared plus 3. If I did a bunch of points there, and in the interest of time, I'm not going to. X squared plus 3, and we'll see this in the next section, is actually, I think it's the next section. It's actually a parabola shifted up 3 units, but I just need to start. There we go. Go far enough over. I need to start at -1. Which is going to give me the point -1, 4. And so I plot a bunch of those points and I get a graph that looks like this. Now notice when I look for the range here, are the y's continuous? In other words, do I use every single y known to man? Or do I skip some? Yeah, in fact I skip these, don't I? I skip in that region. So if I were to do the range, I actually have to write the range in two pieces. This first piece, if I looked at the y's, it's the y's that are less than 0. Remember, I put that open circle, so it's less than 0. Those are all the ones below the x-axis. To do the second piece, that's all the y's. What y's do I use for the second piece? What's the smallest y I use for the second piece?
3.
3. And can I use every value above 3? Yes. So my range, if I write it in kind of inequality notation, is written in two pieces, y less than 0, y greater than or equal to 0. And then I stuck that u in between. What did I mean by the u? Union, yes, union. So you'll want to go back and take a look at that. The last 2 minutes that I want to talk about, and this right here is some solving, is I want to talk about a particular function. The function y equals the absolute value of x. Do you remember from math, from 9th, 10th, and 11th grade math, if you graph y equals the absolute value of x, what it looks like? Yeah, what's it look like? A V. Because it looks like a V, and because it actually, if you didn't know that was the absolute value, and I said, oh, write this, you might think of it as a piecewise function. And in fact, the absolute value of x can be written as a piecewise function. Where this, and your notes talk about this, where this piece is the equation y equals x, and this piece is the equation y equals negative x. And so our pieces are negative x and x. We use the negative x for x is less than 0. We use the actual x for x is greater than 0, and they meet, so I need to put it someplace, and it makes more sense to just talk about the absolute value of 0 being 0 and not the negative of it. 0 as that neutral standing. But notice the absolute value is actually can be expressed as a piecewise function. So something we've been talking about for years and years and years is one of the piecewise functions. And this is the way that you actually do absolute value, right? If I ask you what's the absolute value of 5, you'll tell me that that number is 5. You say keep the same number. But if I ask you what's the absolute value of negative 5, you'll tell me it's 5. You'll tell me make it positive. And mathematically, the way we make it positive is we negate the negative. The way we make it positive is we negate the negative, which brings us back to the positive. So normally I won't take a whole class and I won't go through and painstakingly do the notes, but this section is important enough that you're generally so unfamiliar with it that I feel like I need to talk about it. So what I'm going to ask you to do for Monday, that's the next time we meet, is take a look at the next couple sections. I'm going to take some time and go over some homework problems from those sections. So that's going to be, and I'll ask if there's anything from this piecewise as well. So really look at 2.3, 2.4, 2.5, and we're going to spend the whole class just going through homework problems. Sounds like a plan? Have a wonderful day, and I'll be seeing you.
Are you ready for a fun seminar? Sort of?
It's basically the same exact thing.
Yeah, exactly.
If it's me against
I don't care.
everybody
I'll
else.
I'm gonna be on the side of the least amount of people.
Alright.
Danny, you don't know what you're picking at?
He doesn't